People are coming on. So we were at nitration of benzene. Okay, so I'll go through this very briefly. So this is Simon, in your case, do you understand sp2 hybridization? वो clear है? sp2 hybridization, right?
जी sir.
So I'll just briefly give you the structure of this aromatic benzene ring. And for the rest, remember this is known as an aromatic compound because it has a smell aroma. Most of the organic compounds that have aromas, they have benzene in them. I said now focus on this carbon atom. It's or this one, any one of them. Carbon is making 3 bonds. 3 electrons getting pulled in 3 different directions. So it's making 3 bonds. And the 4th electron is not doing anything. The 4th electron, that's a p orbital that remains unchanged. And each carbon atom is sp2 hybridized. It's making just 3 bonds. It's only bonded to 3 atoms. Like this is a simplified version of benzene. Like you can see that carbon is making or bonded to 3 atoms, just 3 atoms. So what does the 4th electron do? The 4th electron overlaps with the other carbon's 4th electron. But everyone has a p orbital. Each carbon atom has a p orbital. And the end result is they all get mixed up. And you've got a pi electron cloud everywhere on the structure, which is why benzene is represented in the skeletal formula of benzene is a ring. Or in simplified terms, it's basically alternating double bonds. They kind of get mixed up, which is why you get a delocalized electron cloud, which is similar to this one. So the only difference between a normal alkene and a benzene, they're very similar, but they're also very different as well at the same time. The similarity ends over here, that this also has a pi bond. It's a carbon atom making 3 bonds, and the 4th electron overlaps with the other carbon atom's 4th electron. And they overlap above and below, and they end up forming pi bonds. And the same thing exactly applies to benzene as well. But the difference is, in this case, the difference is that the electron density is more distributed, because this p orbital over here not only overlaps with the carbon on the left side, but it also overlaps with the carbon on the right side. So the electrons kind of get distributed, which is why the pi electron cloud over here, the electron density is more distributed and the charge density is lesser compared to alkenes. So in alkenes, the electrons are concentrated at this point, but in benzene, the electrons are like everywhere. They're very distributed. So is this clear? Simon, is this clear?
Yes, sir.
And so that's where the difference happens. And we did the first reaction, which was bromination, which was that if you have a pi bond, what happens in a pi bond is, like if you have a normal alkene, a pi bond has a very high charge density, so it polarizes the bromine molecule. Uske jo electrons hai, they get repelled by the electrons over here, which is why this becomes negative, this becomes very positive, and the bromine positive gets attracted to these pi electron clouds, and the bromine bonds with it. So the pi electron cloud goes missing because this bromine took it and attracted the whole pi electron cloud and attracted it. And the carbocation was formed because this carbon loses the pi electron cloud, and the Br-1 then comes and joins with it. So that was the mechanism of electrophilic addition for alkenes. And we did that. We did the same thing with benzene, that if you have a bromine molecule, the same thing will happen. The bromine molecule will get polarized. The electrons over here in the bond are going to be pushed away. The electrons over here are going to push the electron towards the right. Okay, the arrow over here suggests that the electrons are getting pushed to the right. This side would become negative, this side would become positive, but the polarization is not going to be very strong. The positive charge over here and the negative charge over here is not going to be very strong because the electron density over here is not very high. So what happens is that the polarization is weak. Ye clear, Saim, is this clear?
Yes, sir.
So यहाँ पे ना the polarization is weak, which is why you need a catalyst. So bromination happens with benzene, but you need a catalyst. You need an iron catalyst. Iron from the other side pulls the electron. Like this one, the electrons over here are getting pushed by the electron cloud over here. So the electrons are getting pushed to the right. But at the same time, they're also getting attracted to the right. So there's someone who's pulling the electrons to the right, which increases polarization. So the electrons get attracted over here. This becomes more negative. This becomes more positive. So polarization is not going to be possible with just benzene because the electrons over here, they don't have a very high charge density, which is why the electrons are not getting pushed to the right that much. So you need help, and iron provides that help. Iron pulls the electron from the other side. So the molecule basically breaks into two parts. One becomes -1, the other one becomes +1. The positive bromine goes to the benzene and pulls an electron out of it. So everyone had an electron which were overlapping. So one of the carbon electrons, it got attracted to the positive bromine and bonded with it. So the benzene electron cloud became partial, and it became electron deficient. It got a positive charge, and the next thing would be that it wants its electron back. So the hydrogen, being an electropositive element, the hydrogen likes to lose electrons. So hydrogen is going to quickly give its electrons, and the pi electron cloud would become complete again. The H is going to leave, forming HBr. So the H is going to leave, and that's how the electron cloud would become complete again. So that is the whole mechanism of electrophilic substitution. So when you have benzenes usually undergo electrophilic substitution reactions. They've got, but the only thing is that the molecule of bromine is not going to be polarized enough. So I'm going to discuss the second electrophilic substitution reaction, which is kind of similar. And this one is, okay, in this one, you've got this is known as nitration of benzene. So the first reaction that we did was this one, that it was the summary of the reaction was that benzenes undergo bromination. They also undergo chlorination, but you need a catalyst. You need an FeBr3 catalyst or an FeCl3 catalyst in the case of Cl2. One of the hydrogens in benzene is going to get substituted by bromine or with Cl. And HBr is going to be produced as a result. But in the case of alkenes, you did not have this. In the case of alkenes, where's alkenes? In the case of alkenes, so in the case of alkenes, you didn't need a catalyst because the electron cloud was powerful enough, and the electrons were very concentrated at a very specific point that they would attract or pull the positive bromine, and they would repel the negative bromine themselves. They didn't need any help from outside, which is why this would happen at RTP, but in the case of benzene, that will not happen at RTP. But anyways, the next thing about nitration of benzene, and that is, when you have nitration of benzene, in nitration of benzene, the electrophile is, this is what we were discussing yesterday, the electrophile is NO2+1. The temperature is kept at 50 to 60 degrees centigrade, and concentrated sulfuric acid and nitric acid are used, and kind of the same reaction happens, and nitrobenzene is formed. So you just get this is the overall reaction, that you get a substitution as a result. The mechanism of this reaction is, so we're going to talk about the mechanism of this reaction. So the mechanism of this reaction is kind of the same. What happens during mechanism is, okay, the first step number one is the electrophile is created, or the electrophile is produced. So that is step number one. The electrophile is produced. And how is it produced? The concentrated sulfuric acid or the concentrated nitric acid, they react together. And they're going to react together. The reaction is going to be H2SO4, and you have to remember this reaction. So the reaction is going to be H2SO4 reacting with HNO3, and the product is going to be NO2 plus 1 and 2 HSO4 minus 1 ions are produced. And the other thing is that there's going to be H3O plus 1 ion that is also produced. So that is step 1. And they're going to ask you for this reaction. Just make sure this is balanced. There's 1 N, sulfurs, 2. I count the hydrogens, that's 5. Over here, you've got 5 hydrogens. So the oxygens are also 8 plus 3, that's 11. 2, 4, 6. No, sorry, 2 and 8, 10, 10 plus 1, 11. So everything is balanced. So the first step of the reaction is that an NO2 plus 1 electrophile is going to be created. And that's your electrophile. That is produced. Which is why you add concentrated sulfuric acid and nitric acid. Now the next step is, like, if I copy one of the benzenes. So the next step is, now I'm going to come to the mechanism of the reaction. So I'll just copy this benzene. So the mechanism of the reaction. Now the thing would be that this benzene comes in. The NO2 plus 1 has a positive charge. So the NO2 plus 1 is going to be very strongly attracted to one of the p orbitals of carbon. So every carbon atom, its 3 electrons are busy bonding. The 4th electron is making pi bonds. It's overlapping with all the other ones. So the NO2 plus 1 is going to come in, and it will attract one of the p orbitals of carbon and bond with it. So the next step is, step number 2 for the reaction is, and let's make step number 2 over here. So step number 2 of the reaction is that you've got this NO2 plus 1 coming in. So this electron over here, it's going to disappear because, so this electron over here, it's going to disappear. Why? Because the NO2 plus 1 is going to take it. The NO2 plus 1 is going to attract it, and the NO2 plus 1 is going to bond with it. So the carbon over here is going to bond with the NO2 plus 1, and obviously the plus 1 charge is going to disappear. But the benzene will now get a positive charge. The benzene electron cloud is now going to get a positive charge. Why? Because somebody took its electron, right? So previously you had a full, complete electron cloud, but now on one of the carbon atoms, the electron is gone. Is that clear? Sam, is this clear? Nadeem? Alicia, is this clear?
Yes, sir.
And what's the next step? Now the benzene electron cloud is electron deficient, so it needs the electron from somewhere. And H is the one that is very willing to lose electrons. H is a very H always likes to form H plus 1. So H is the one that's going to give the benzene electron cloud its electrons. And where will the H go? Because previously there was HSO4 minus 1 that was produced. So the HSO4 minus 1 is the one that's going to accept that H. It's going to get attracted, like if the H leaves, it becomes H plus 1. The H plus 1 would join with HSO4 minus 1 to form H2SO4 back again. So the last step is the electron cloud is going to, it's going to reform. So let's copy everything. And the last step of the mechanism would be, so the last step of the mechanism would be that that this H leaves, H plus 1. and it joins with HSO4 minus 1 to form what? To form H2SO4 back again. So the HSO4 minus 1 combines with the H that has left. I made it in the wrong side, just a second. This one. So this H over here is going to leave its electrons, and it's going to go and join with the HSO4 minus 1. And this thing would become H2SO4. What happens to these two electrons? These two electrons form the p orbital back again. So the p orbital, so the benzene gets its pi electron cloud back. So those two electrons are now again here, and they would start to overlap. The electron deficiency of the benzene it's going to become complete again. And the overlapping would start all over again. So the benzene electron cloud would become stable again. It's going to get the electron. It's going to get the electron back. It's going to get the electron back. And as a result, you've got NO2 now connected. So the NO2 is now joined with the benzene. So instead of the H, you've got NO2 that's attached to it. And that's your substitution that has happened. So the benzene electron cloud becomes complete again. So that's the whole mechanism of the reaction. Is this clear? Is this clear? Yes or no?
Yes, sir.
Yes, sir.
So that's the entire mechanism. So it's kind of similar to what happened in bromination, except that in bromination you needed a catalyst. Like bromination was very similar, but the bromine molecule wasn't an ion. It wasn't a positive charge. You had to make it a positive charge. So you had to somehow push these electrons. So which is why you needed a catalyst on the other side. But that's so this was slightly difficult. So you needed a catalyst. But even in this case, you still kind of need a catalyst, because who's the catalyst? The H2SO4 is the one that's acting. Sohail, आपका वो बात. Just hold on 1 second. Hold on 1 second. Not sure why this. To leave this, I think Zoom is hanging up. अच्छा, so this one. एक सेकंड फिर से. अच्छा, can everyone hear me?
Yes, sir.
So there's some issues with Swell. So this one is we've got this reaction. You have to remember the mechanism, everything. So remember the two main electrophilic substitution reactions that you have to study. One is nitration of benzene, and NO2 plus one is the electrophile that acts as the electrophile and then goes and substitutes one of the hydrogen atoms. And Sohail, I've got mic on, baby. It's still hanging up. So I don't know what's happening. So this one. You've got so this is the whole mechanism and of the reaction. Now, the next thing we're going to study is so remember, these are the two. Electrophilic substitution is one of the main reactions that you need to study. Now, this is only for benzene. What we have studied only applies to a specific normal benzene. And remember, benzene is going to have a lot of derivative compounds. Benzene is going to, so we're going to study electrophilic substitution of benzene related compounds. So what's a benzene related compound or a benzene derivative? It is that normally benzene has 6 hydrogen atoms. Actually, one thing I did not draw the exam diagram, which is going to be this one. So let me draw the simplified version, because this is obviously not the mechanism that you're going to draw in the exam. So the exam mechanism, the simplistic mechanism for that would be that you'll have a benzene. You'll just draw the skeletal formula. Obviously, you're not going to draw the whole 3-dimensional thing. So it's going to be the skeletal formula of benzene, and the NO2 plus 1 is going to come in. The NO2 plus 1 is going to be interested in benzene's electrons. And the next step would be that this benzene electron cloud would become partial. So next step is that your benzene electron cloud would become partial. There's not going to be an electron cloud on the last carbon atom. The NO2 is going to come in and it's going to bond with benzene. And there's going to be the H. In the next step, the H will lose electrons to the benzene electron cloud. And the HSO4 minus 1 is going to accept that H. So the electrons from HSO4 minus 1 are going to be attracted to the H. And the last step would be that the benzene would be reformed. So that is what you're going to draw in your exams, not the first one, obviously. So the H over here would be lost. This thing would have NO2 attached to it. The benzene electron cloud would become complete again. And this HSO4 minus 1 will turn into H2SO4. So that's the mechanism. It's the same above mechanism. And this is what you're going to draw in your exam. You can remember, they're going to frequently ask this. And these are the 2 steps of the reaction. As in, again, I made the mistake. I did all the changes over here. This one is in the middle. So that's your exam mechanism. Okay, and don't miss any charges. Everything has to be exactly the same. So you have to memorize this exactly the same way. I said now, so remember, this is just exactly the same thing that we just sketched above. It's just that one was a more detailed version. This is what you're going to draw in your exam. Now the next thing is, let's talk about benzene derivative, and I'm going to stick to the electrophilic substitution of the same one, bromination and nitration. We're going to stick and discuss these two. Now, the first thing is, let's introduce benzene derivative compounds. Now, a benzene derivative compound is something that has benzene attached to it. So you've got this benzene. Now, if you look at benzene, it's got 6 hydrogens, but a lot of times it's not going to have 6 hydrogens. There could be anything attached to it. Now, in the skeletal formula, you don't show the hydrogens. You never draw hydrogens in the skeletal formula, but remember, when you draw the skeletal formula, there's 1 hydrogen over here, 1 hydrogen over here. Each one of the carbon atoms at these points, they have 1 hydrogen attached to them. You don't always show, I mean, in the skeletal formulas, you don't show hydrogen atoms. So a benzene derivative is that sometimes instead of the hydrogen atoms, there could be something else attached to it. So the first one, we already did a few of them. Like over here, instead of the 6 hydrogen atoms, there's an NO2 attached to it. So that's known as a nitrobenzene. So we're going to do all of them. There could be a bromine attached to it. So the first one, we're going to start with arenes. Arenes are that they could be, instead of the hydrogen atoms, there could be alkyl chains that could be attached to it. For example, you've got CH2, CH3, and there could be more than one alkyl chain. So that's your arene. And also remember, benzene compounds, they don't usually have a systematic naming mechanism. The nomenclature doesn't really fit or work with benzene. Most of them have generic names. The reason they have generic names is because the systematic naming usually fails. So what you do is you just, I mean, some of them are named after different people, basically, or because of their. So that's, once again, that's what. So that's what an arene is, which is basically a benzene attached to an alkyl chain. And the name of this molecule is going to be ethyl benzene, because you've got an ethyl group attached to it. So this one is ethyl benzene. You could have methyl benzene, you could have propyl benzene. So you could have all sorts of benzenes. You don't have to learn all the names. The simple ones, you should be able to, I mean, you should know what the simple names are. Like this one is ethyl benzene. This one, like if I draw another one, let's say I take out the CH2 and there's just CH3. So this one would be called methyl benzene. So just the simple ones. And even what happens is most people don't even call it methyl benzene. So I'll just give you an example, like the one that we did for nitrobenzene. I mean, if I search toluene, that's methyl benzene is basically the name of methyl benzene is toluene, right? So that's what I'm trying to say, that every compound is kind of named differently. Like there's no systematic nomenclature. So we're going to stick to the simple ones. Like we'll just call it methyl benzene. That's about it. So the simple ones, you can kind of name them. Sam, is this clear?
Yes, sir.
ठीक है. अच्छा, उसके बाद है कि you've got so that's arenes, and you can have multiple. I mean, remember you have a benzene, so you've got 6 hydrogens, and you could have multiple different groups attached to it. Instead of the 6 hydrogens, you can have anything attached to it. So that's arene. Arene is when you've got a carbon chain attached to it. Then you have another one which is known as, I mean, like the chlorobenzenes that we did. So if you have a Cl attached to it, so I'll just go through this quickly. This one would be called a chlorobenzene. And you could have multiple. So this is known as a halogen derivative. Sometimes they do some numbering as well, but remember, even the numbering usually doesn't really work with benzenes a lot of times because it's a cyclic compound. So maybe there might be 2 Cls attached. So what you do is that you take the shortest distance. Like if this is 1 chlorobenzene, the other one would be 1, 2, and it's on the third one. So it's 1,3-dichlorobenzene. Dichloro means that there are 2 of them. So if this is 1, you take the shortest distance. This is the third one. So that's basically 1,3-dichlorobenzene. Then you have.
I mean, how do you attach it? क्यों हो रहा है? क्यों हो रहा है?
नहीं, मैं वैसे बता रहा हूँ ना कि बेंजीन है ना, कुछ भी अटैच हो सकता है ना. It could be anything that could be attached to this. Why just hydrogens? Like we did the mechanism, right?
I just came in, so मुझे नहीं पता कि what were you guys discussing?
नहीं, I'm just saying that they are derivative compounds. So you've got like we did the mechanism कि bromine, इबरार bromine attach हो गया ना. So what happens कि instead of the 6 hydrogens, you still have a benzene, but you've got a bromine attached to it, right? So this is known as a benzene derivative compound. It's something. It's a benzene plus something. Okay? It's just think of it in the same way. Like every carbon atom, like previously you did organic chemistry, everyone had a carbon chain, right? Sometimes there was an OH attached to a carbon chain. Sometimes there was a carboxylic acid group attached. Sometimes there was an aldehyde group attached. Sometimes there was a bromine attached to the carbon chain. So it was the same carbon chain, but so the functionality would change if there's some group attached to it. Is that clear? So this is no longer going to act like a benzene exactly. This is going to be something slightly different from benzene, just slightly different from benzene. Do you get my point?
Yes.
Okay, so think of them as functional groups, getting attached to this aromatic benzene ring. So if you've got a carbon chain attached to it, the functional group, you're going to call it an arene. You're not going to call it benzene. If you've got a halogen attached to it, you're going to call this chlorobenzene. So this is going to behave differently compared to a benzene, compared to a normal benzene. Its reactions are going to be different. Just like an alkane and a halogenoalkane, they are different. They've got different reactions. In the same way, a benzene and a chlorobenzene are going to be different. The next one, so I'm just introducing some of the more important ones. You've got phenols. Now, a phenol is like an alcohol. It's just a benzene with an OH attached. So it's kind of the same thing, except now you've got an OH attached to it. So instead of Cl, let's say you've got an OH attached. And that's a phenol. Now remember, phenols are not alcohols, and they're also not benzene. They're a separate functional group. A phenol is going to behave differently compared to an alcohol. So don't think of it as an alcohol. And we're going to do the reactions later. So that's what a phenol is. And it will also behave differently compared to a benzene, like the benzene that we did. Then you're going to have phenylamines. So a phenylamine would be an amine attached to a benzene ring. So let's say you have, instead of the Cl, you're going to have NH2. So again, treat it as a different functional group. A phenylamine will behave differently compared to an amine as well as a benzene. It's going to behave differently. You also have benzoic acid. So benzoic acid is So a benzoic acid is a benzene with a carboxylic acid.
So do we have to memorize them or keep them in mind?
नहीं, the introduction there, no, because remember I told you that there's no systematic naming for benzene derivatives. Just like, I mean, previously you had systematic naming. Like if you had a carbon chain and there was an aldehyde attached, so it had a systematic naming system, right? Benzene functional groups, they don't really have a systematic naming. Okay. I mean, the simple ones you can name, like this is benzoic acid, like, but molecules can get really complicated. So which is why they don't follow a very specific systematic naming system. So this one is benzoic acid, and you'll have benzaldehyde. Benzaldehyde is obviously just by the name. It's a benzaldehyde is basically a benzene with an aldehyde group. So instead of the Cl, there's going to be an aldehyde group. Okay, don't worry too much about naming. Is there anyone I'm missing? You've got so I think that's pretty much it. Okay, you don't have to go into that much detail. What I'm going to go into detail about is it's this thing. When you attach these functional groups, what happens to the benzene electron cloud? And this is something that's more important. So remember, you can have different functional groups, just like aldehydes, ketones, carboxylic acids, OH groups. All of these things are halogens. All of these things, they can get attached to a benzene. Like one of the hydrogens over here or anywhere can get substituted and can be replaced by any group that comes to your mind. But what's important is the groups are divided into two parts. There's a group called the 3,5. We'll start with the 2,4. There's a group called the 2,4, and I'm going to put 6 in the bracket. It's usually just referred to as the 2,4 directing group or groups. Huh? So so you have 2,4 directing groups. Now, which groups are 2,4 directing groups? Electron donating groups are the ones that have a tendency to donate electrons. So which have an electron releasing effect. So
ये 6 बीच में आपने क्या लिखा है? 2, 4, 6 directing groups.
वो मैं बताता हूँ ना. 6 मैंने bracket में लिखा है because it's usually referred to as 2,4 directing groups. But sometimes, I mean, the more correct way is actually 2, 4, 6, but usually it's just referred to as a 2,4 directing group. I'm going to explain what a 2,4 directing group is. So let's bring in the benzene. Where's our benzene? Let's bring in this benzene over here. And I'm going to explain what will happen if you attach a particular group to this. So if you attach a particular group to this benzene, so your benzene, we have the benzene with us. And forget this. So leave the mechanism. Now what I'm going to do is I'm going to attach a carbon chain instead of one of the hydrogen atoms. So I've got CH2, and CH3. So right now, this is all that I'm going to discuss. Now, based on your AS knowledge, you should know that alkyl chains have an electron donating effect, that they push electron densities away from them. They push it onto any group that's attached to it. So I've got an alkyl chain, and that alkyl chain has an electron donating effect. So it's pushing the electron density towards the benzene. So what will happen is that the electron density will slightly increase on the carbon atoms over here. The electron density over here on these carbon atoms would slightly increase. So previously the benzene electron cloud was very evenly distributed. But now because of this group that's attached on one side, it's attached on the right side. And that is pushing electrons onto the benzene. So the electron density would be slightly higher on this side. Is this point clear to everyone?
Yes, sir.
Okay, so that's the main difference. Like if you attach a group, the electron cloud that was formed on benzene, it's going to get disturbed, and the electron density would be slightly higher on one side. And because the electron density is higher on one side, all the other electrons, they would get repelled because of the high electron density, and they will all get pushed to the other end. So that means the electron density would also be higher at the extreme opposite end. So this is what's happening. You attached a benzene, so you attached a carbon chain. Carbon chain has an electron donating effect. If it has an electron donating effect, it's going to push the electron density, and the electron density on the benzene on one of the sides is going to increase. And all the other electrons in the electron cloud, they're going to get repelled because of the high electron density on this side, and they will get repelled to the exact opposite side. So the benzene electron cloud is no longer evenly distributed. It's got electron density higher on one side and also higher on the opposite side. Is this point clear?
Yes, sir.
So on which of the carbon atoms is the electron density higher? It's higher. I mean, if this is carbon number 1, we're going to give this carbon number 1, the one on which the carbon chain got attached, alkyl chain got attached. So the neighboring carbon atom is carbon number 2, right? So it's higher on carbon number 2. On carbon number 3, it's not high. At carbon number 4, it's higher. At carbon number 5, it's not high. At carbon number 6, it's higher. So basically, the electron density is higher at positions 2, 4, and 6. So think of this as carbon number 1. It's pushing electrons, so the electron density is higher on these two carbon atoms. So if this is 1, then the next one would be 2. So it's higher on carbon number 2, not high at carbon number 3, higher at carbon number 4. So I'm going to give these positions. So this is 2. The extreme other end is 4. This is 5, and this one over here would be 6. Is this idea clear? We'll discuss the importance of the idea.
Yes.
So we're going to discuss the importance of the idea later, but why is that important? But just remember that previously, if you had a benzene, the electron density was evenly distributed. But when you attach a group, especially a group that has an electron donating effect, like a carbon chain always has this effect that it pushes electron density onto anything that's attached to it. So the electron density would be higher on this side, and it would be higher. And the other electrons, because of the high electron density on this side, will get pushed, and they will become concentrated at carbon number 1. So electron density is higher at carbon number 1. It's higher at carbon number 2. It's also higher at carbon number 6. The reason you don't use the word 6 is because counting can be done from either side. It could be anti-clockwise counting or clockwise counting. So either way, I mean, if you count from the other side, that would be carbon number 2, right? So people usually don't mention 6. But otherwise, the proper way is that it's higher at 2, 4, and 6. Okay, so we'll build on this concept. And this is the important concept. Remember, we're going to link electrophilic substitution to what's happening to benzene when something gets attached to it. Okay, so let's continue in the next class then. Is this clear so far? Alicia, is this clear? Right? Saim, clear?
Ji, sir. Thank you.
Sir.
Okay, take care. Hafiz.
So I just wanted to ask, where can I get the recorded lectures from?
मैं भेज देता हूँ, ठीक है, जो पिछले थे 2-3. ठीक है, चलो, ओके, अल्लाह हाफिज.